Good morning, Year 12s. What we're looking at today is optimization. Now, optimization is really quite difficult to teach because it draws on so many different areas of maths. From calculus, it's important to remember that we can optimize, meaning find the maximum or minimum, by recalling the first derivative and where it's equal to 0, and then having a sign change. Positive to negative is a maximum, negative to positive is a minimum. So we've seen this before many times, but now it's about putting that into use. So I thought the best way to do this is just go through a couple of different, slightly odd sort of questions, and you'll come up against more and more in the textbook, and basically the more practice you do, the more comfortable you'll get at this type of problem solving. Here, a rectangle is bounded by the x and y axis, and the graph of y equals, that would read y equals 6 take x on 2. Now, what length and width should the rectangle have so that its area is at a maximum? So what they're basically saying is we can put a point anywhere on this line, and we're trying to find something that maximizes the area. So it could be that red one, the green one they've drawn, or any other point along that line. I would start off by noting that the point on the line here would be equal to x across 6 take x on 2 up. And therefore the area of the rectangle is going to be equal to the length multiplied by the width. Or the area is going to be equal to 6x take x squared on 2. Then, if I want to find so basically the idea is to write these as an expression for a variable. Once you've got the expression in one variable, you can differentiate and find a maximum. You can see that there's a quadratic, so we'd expect to be doing that because it's got a negative leading coefficient. The question is, well, what value is x here? And now we know calculus, we can differentiate the area with respect to x. And what we find is that will then be 6 take 2x on 2, which is the same as 3 take x. And we want to find, well, where that is equal to 0. And that's equal to 0, clearly, when x is equal to 3. So when x is equal to 3, it's suggesting this is maximized. And what we can do is we can check the sign diagram. So we can go along here and say 3, well, what is the derivative change either side of 3? Clearly it's going to be, if it's less than 3, positive, negative, which explains the positive, negative slope. So this here is a max. And then to sub in the point, well, 3 take 3 on 2 is 1.5. And you can see they've almost drawn the maximum because they wanted to maximize it 3 in, which gives us 1.5 up. And that would be the maximum area you can get. So that would be the length and width. 3, 1.5. 1.53 will do. Right. Another problem, also graphical. Find the point on y equals x squared closest to the point 3, 0. Now that seems quite odd, but the point 3, 0 is here. And then we want the point y equals x somewhere on here. Now somewhere on this graph has the point x, and then the y coordinate is x squared, because y is equal to x squared. So really we're looking for the distance between these 2 points, the point 3, 0 and the point x, x squared. Now, if we're looking for the distance between 2 points, we should be thinking distance formula. So, distance formula, and don't stress about memorizing all the formulas. In tests, SACs, exams, generally be given these type of formulas, or they'll be in the formula sheet at the back. So, for example, I can tell you that distance is equal to y2 take y1 squared plus x2 take x1 squared. And then what you need to be able to do is sub in and solve. So subbing in and solving here looks like, well, the distance is going to be equal to the square root of y2 take y1, which I'm going to say is x squared take 0 plus x take 3 squared, and that's the distance. All right. Now we have an expression for the distance. We want to try and minimize the distance. So to minimize the distance, I would be expanding and simplifying under there. X to the 4 plus x squared minus 6x plus 9. And then I'd be differentiating this. So the change in distance with respect to x looks like a half x to the 4 plus x squared minus 6x plus 9 to the minus a half multiplied by the derivative of the inner, which is 4x cubed plus 2x squared, go over here, minus 6. Okay. Then we want to solve, for when that's equal to 0. That there's a times. Alright, so 0 equals the above. And clearly, we're not asking you or expecting you to do that algebraically necessarily. Calculator is an excellent way to go about this, so throw it into Solver. Right. And if you throw it into Solver, the solution comes out as x equals 1, which is pretty neat, because what that means is that the closest point from 3, 0 to the line y equals x squared hits here at when x is 1 and then y is 1 squared, is 1, 1. Neat, huh? Alright, here is a classic one from your textbook. Cover 6, stems. Basically, there's a boat 5 kilometers out to sea. AC is a straight line to shore, which is 6 kilometers long. Peter can row a boat at 8 kilometers per hour and run along the beach at 17 kilometers per hour. Suppose Peter rows directly from A to some point x on the beach, such that AX is little x kilometers out. Explain why little x has to be less than 6. Well, because the beach is only 6 kilometers long. You can write that. So, therefore, x cannot be greater than 6, otherwise it would be landing out here somewhere. Alright. Then, show that the total time that Peter takes to row along x and run along the beach to the sea is given by this function here. Now, this is a useful triangle that you're probably expected to know. Speed, distance, time. From physics, you've seen it before. If you want time, you basically just cover time up with your hand, and time is equal to distance over speed. That's a t equals distance over speed. So, Peter's run is going to be in 2 portions. There's this leg, and there's this leg. So in green first. So here, the time taken for him to complete this is distance over speed. Now, distance is interesting here because distance will be equal to the square root of this length here, 5 squared, plus x squared, which can be written as distance is equal to the square root of, and when you're doing these, keep an eye on the end game. So for example, if they write x squared first, it's worth you writing it first as well. X squared plus 25. Then speed is 8 kilometers per hour. So this big chunky pen here, time will be equal, along the green stretch, is equal to the distance, x squared plus 25, over the time it takes him to run it, sorry, the speed he runs it at, is 8 kilometers. In blue, very simply, this distance here is the 6 kilometers of the beach, subtract the x. So that there is 6 take x in distance, and therefore the time it takes him to run it is 6 take x over the speed he can run it at, which is 17 kilometers per hour. He's pretty quick. Alright, so the total time is these two added together. Find x such that dt dx is equal to 0, explain the significance of this value. If you differentiate that with respect to x, and I'm sure you all can, then when it's equal to 0 will be the minimum time it takes him to complete this journey. So x is how far he should aim up the beach in order for this journey to have a minimum length of time. Yeah? It's, well, the answer's in the textbook, but have a shot at it yourself. Thank you and goodbye.